Thanks for the introduction, and thanks everyone for showing up for my talk. Owing to jet lag, I'm probably going to talk a little bit slower than usual, which may end up being to your benefit. So indeed my title is Topology and Time-Dependent Quantum Systems today. And the heroes of this talk are Mingwu Liu, who was a senior postdoc in the experiment when this work was done, as well as Graham Reid, who had a really great idea that turned into a second paper that will be the second half of my talk. What I'd really like to highlight about this slide, in addition, is the sort of bottom three projects that are listed down here, all of which are collaborations with other senior experimentalists in the Joint Quantum Institute. So if any of you are, let's say, graduating PhD students and looking for postdocs, we certainly have opportunities in all these kind of things, working with not one but several cool senior people. So I want to lead off with a little bit of an introduction about topology in physics. And I'd like to make a point here that we don't have to just talk about abstract quantum systems to think about topology in physics. So, and the second thing I'd like to highlight is what is and is not topology. So what I'm plotting here are, well, basically three simulations of the cosmic microwave background that would have been seen for different configurations of the universe, whether it be open, flat, or closed, meaning is the curvature locally saddle potential, flat, or dome-shaped. And what I want to distinguish even in this slide is we can ask questions about the local curvature of the manifold and contrast it with the topology of the overall system. Now, topology is not confined to ultra-large things or quantum things. Topology can exist in between. And when we think about topology, what we're asking are questions about the system. They're invariant under small differential changes. So one of my favorite experiments about topology is realizing knots, in this case, this ring of bubbles, as a vortex knot in water. And the enterprising experimentalists made all these sort of hydrofoils, as pictured here, and blasted water past them to make various knotted configurations, or you can see looped configurations in the water. So sort of on mesoscale, on tabletop scale, one can create topology, in this case, not topology, in physical systems. And an analogous example is plotted on this side, creating topology in the field of the electromagnetic radiation field of a laser, where holographically the zeros of this field were produced to trace out the same trefoil knot as is also created in this water. All right, so hopefully these are not sort of the usual examples of coffee cups you usually hear about when people try to introduce topology. Again, these objects, these knots, are also robust against differential transformations and are indeed topological entities. All right, so to sort of think about this very clearly, we're going to be in this talk thinking about both geometry and topology. And this is sort of the classic picture you'd have for this. So if we think about this torus, the Gaussian curvature, that is, the second derivatives along these two directions, are the local geometric property, which when integrated over this manifold by the Gauss-Bonnet theorem gives you the genus of the surface. But more generally, we typically characterize topological invariants in terms of integrals such as this one. So this is describing an integral over a 2D manifold with some kind of tensor defined upon this manifold and then given by integrated over an appropriate measure. In the Gauss-Bonnet theorem, this tensor is no more than the tensor elements of the Gaussian curvature, which is derived from the manifold itself. But an important point is that this tensor does not necessarily need to be derived from the manifold. And what we're going to be thinking about here, there's going to be a quantity embedded in the manifold, and we're going to study the mapping between the manifold and the space of the embedded object. Okay, so specifically it's going to be the quantum geometric tensor, describing the change of quantum states across a manifold. Now, for those of you who don't think about topology all the time, this is probably seeming a little bit abstract. But we all know about this, actually. In undergrad physics, every one of us learned about Gauss's law. So if you simply replace F mu nu with an electric field in tensor form, this wedge project with a surface norm, we know that integrating over this surface counts the number of charges in the inside of the surface. So an example of this complicated seeming idea is just Gauss's law. All right. So although it's an example of it, in fact, it's apropos to the most common topological invariant that you hear about, which is the Chern number, which indeed can be understood in terms of counting charges inside a generalized manifold. All right. So I want to give a super quick primer to the physics you guys need to know to appreciate this talk. I'm going to assume that everyone in the quantum center is fully up to speed in two-level systems. So I've omitted the slide introducing two-level systems. But I'm not going to assume that everyone here knows all about condensed matter physics. So I'm going to give a very, very brief sort of discussion about the tiny amount of condensed matter physics that you need to know to sort of get your footing for what I'm going to talk about. So what I want to think about is some kind of periodic potential. One of the amazing things about cold atom physics is that we can make the simplest potential you can possibly make. So we typically think about periodic potentials as being synthesized by many Fourier components, such that the lattice is invariant under discrete transformations by the lattice period A. And we can make the simplest example, which is a sinusoidal potential. The lattice I'm going to talk about today has one additional Fourier term, giving it more structure. Okay, so we're going to think then, what can this lattice do? Well, it can scatter atoms or whatever off of it, and the change in momentum has to be given by the reciprocal lattice vector, that is 2 pi over a of this lattice. Therefore, we couple together atomic states whose momentum difference is 2 pi over a. So the way to think about this then is if the lattice were absent, the dispersion relation of these atoms would of course be parabolic. And now what we do is say we're going to couple states whose momentum differs by 2 pi over a, which in these units is -1/2 to 1/2. So for example, this state here would attempt to couple to that state there. But that's off resonance, so not much is going to happen. However, the state intersecting this gray line will couple resonantly with the state connecting that gray line, giving rise to band structure of this form. So maybe those of you who don't do this every day can dredge up from your memory of condensed matter physics the extended zone scheme, where we have sketched a parabola here spaced by 2 pi over a along this direction, another one along that direction. And at every point these intersect, a small gap will open up in these dispersion relations, separating out the block bands of the system. Right? So coming back to topology now, what I established in my previous slides is we need to understand the motion of something across some manifold. And the manifold I'm going to be thinking about today is going to be two-dimensional. One of those dimensions is going to be the dimension consisting of these crystal momentum states. Now we need to have closed loops, as we had in the torus. And in this accounting, this point here at -1/2, in fact, is exactly the same quantum state as at +1/2. So traversing this trajectory there constitutes tracing out a loop in some parameter space. And in the abstract, what we're going to be doing is looking at the change in the orientation of quantum states in their Hilbert space as one moves about these trajectories in state space. All right. This picture is a rendition closely approximating the lattice we're actually going to be studying. And the take home for this is that this lattice is a bipartite lattice with sites we can label effective pseudospin down and pseudospin up, so A sites and B sites. When these are tilted, as I've sketched here, this forms a double band situation where the lowest band is predominantly the up state and the higher band is predominantly the down state. And this effective two-level system, motion in the lowest band, corresponds to changing the orientation of the state in a two-level pseudospin space and therefore moving about on the surface of a Bloch sphere as a function of the horizontal axis, which is crystal momentum. And as we go through the talk a little bit more, we're going to touch on a bit more detail about exactly what these states are, but this is the abstract picture you should begin to carry around in your mind. All right. So moving on from that, I gave some sort of high-level examples of topology in physics. In the context of band structure and condensed matter physics, topology appears all over the place. It appears in quantum Hall physics, both integer and fractional. It appears in what are now called topological insulators, which are typically a time reversal invariant version of these things, and sort of semi-strongly interacting systems like P-wave superconductors that are basically mean field versions of topological insulators. And these are sort of cartoons of fractional quantum Hall systems, P-wave superconductors, and topological insulators. The thing to take away from this slide is the things in red. And the things in red are features that aren't native to our cold atom system. So for example, if you apply a magnetic field to a cloud of ultracold atoms, you simply have the Zeeman effect, and not what you want, which is a Lorentz effect. So the introduction to, my introduction mentioned artificial gauge fields. That was the point of that whole exercise, was to introduce that kind of term. Similarly, topological insulators need complicated band structure engineering of the spirit I'll talk about today. And P-wave superconductors need some kind of effective P-wave interaction to be birthed from our S-wave interacting systems. If we now turn our attention to topological insulators broadly construed, including integer quantum Hall effects, this is in fact, at least from a theoretical point of view, a solved problem. So this chart, which we're going to look at, tells you everything you could possibly know about these topological systems. They're labeled by a class, and I'm going to call this class a fancy name. These are symbols that only a mathematician could love, A, A3, BD1, and so forth, that label all the possible configurations of symmetries that are possible in these systems. So we're going to think about time reversal, particle hole, and a chiral sublattice symmetry later on in this talk. And you can see that these combination of symmetries identifies this class. And lastly, this sort of topological periodic table includes the dimension of the system. And once you know these things, you can say, well, if I'm in class A3 and I'm in one spatial dimension, I can have a topological index as an integer, a member of Z. So you may have heard of Z2 topological invariants like that one. That might mean the topological class can only be 0 or 1. Right? So this is it. And you say, well, why are you studying this if this is it? I didn't mention that this is equilibrium. So the assumptions that go into this characterization assume you're studying equilibrium physics. So the question we're going to get at today is, what can you study if now you open your state space or to dynamical systems? And we're going to look at this in two ways. One way is going to be Floquet. In this sense, for those of you who are not familiar with the Floquet description, we'll have a time periodic Hamiltonian. And just like you can characterize band structure in terms of something that repeats in terms of the reciprocal lattice vector, in a Floquet system, you can have eigenstates or quasi-eigenstates that repeat every 2 pi over the time, or repeat over the period t, and have an energy 2 pi over that period t. This allows new kinds of topological invariants, sometimes called anomalous Floquet insulators. And some of the neat work is both described theoretically here as well as observed experimentally in Monica Edelberger's group. We're going to be looking at a 1D version of this, giving a 2D Floquet winding number. A second and broader problem you can ask is, what about just freely evolving quantum systems? What if you start out in a state described by some topological invariant and quench to a new Hamiltonian, maybe that has different symmetries, and allow it to evolve according to that? What can happen? And we were guided by this theory paper from Max McGinley and Nigel Cooper that sort of showed us a way to think about this problem. And in fact, I think this is a good slide to mention Graham Reid's unique contribution here. So I don't know how many of you are experimentalists, but very rarely do experimentalists get tied up in ideas like gauge invariance, because we measure things in the lab. Everything's gauge invariant. But it turns out a lot of these theory descriptions have weird gauge dependencies built in that disappear upon measurement but seem intrinsic to the theory. So Graham was obsessed with trying to understand and disentangle the meaning of these gauge invariant things. He took a great deal of data on the topic. Then, by what can only be described as amazing luck, he read this paper from Nigel and Max and discovered that he had taken just the right data to in fact demonstrate their experiment. And they even had in their SM, supplementary material, figures predicting exactly what data Graham had taken. So very rarely does this line of inquiry lead something that fortuitous. So then we had some Zoom calls with Max and Nigel, took one more set of data on a different topic, and that led to Graham's paper. So, you know, this is a great example of students. Hopefully some of you guys have some great ideas and choose to ignore some of the things your advisors like me would say and have the big contribution like this. All right, so I'll be talking about this one first and then free evolution second. So I have two slides here. This next one is something I typically do in colloquia. So I've said, okay, we're going to use cold atoms to do this, and I haven't said much about our physical platform. For those of you who have been to cold atom talks before, particularly colloquia, it often goes something like this. There's some big thing like a high temperature superconductivity that we want to study, but instead we're going to try to realize it with ultracold atoms, maybe BECs. And once we've done that, of course, condensed matter experimentalists and theorists are creative and they come up with something new like quantum magnetism, and that too we can perhaps try to do with cold atoms. But ever creative are physicists, and maybe they build devices that can realize quark gluon plasmas. But once again, our cold atom systems perhaps can shed light on that as well. And should we just add butter to every physical idea and make it better with Bose condensates? And the answer is cold atoms can shed light on a lot of physical phenomena, but these are very, very simple physical systems, and they often don't have the richness that's present in larger scale, typical physics. So what do we get by using cold atoms, and what price do we pay by using cold atoms? Well, cold atoms can be thought of, as I will in this talk, as good materials for the reasons that numerous properties can be controlled and measured on virtually every timescale relevant to the experiment. Okay. That means that we can change some property like the lattice depth instantaneously and actually have the outcome you learn in quantum mechanics class of the instantaneous approximation, or we can tune parameters slowly and mimic the adiabatic approximation. Secondly, our Hamiltonians within the energy domain we study are incredibly simple. And what this allows us to do is have like really serious collaborations with theorists where we expect to give real parameters to our theory colleagues. We expect their calculations, if done correctly, to lie on top of our experimental data. And this is quite different from condensed matter physics generally, because one has to have effective field theories in that domain. On the other hand, cold atoms are very bad materials. Our samples are short-lived and live in vacuum systems, so it's very difficult to make devices out of ultra-cold atoms. You can't connect wires to them. And once you've measured these systems, typically the measurement is destructive at minimum in the sense that your atoms have been expelled, and it can be destructive in the sense of quantum measurement as well, that you can distill all the information out of them. And I think, however, the most challenging thing is that all the interesting features at this point are added by hand. Optical lattice lasers, more lasers to create artificial gauge fields. Maybe you're going to have a Feshbach resonance thrown in. Maybe you're going to make some molecules. These experiments get complicated. And that's the price you pay for simple Hamiltonians. All right. So in that context, broadly speaking, we have three categories of tools that we can employ in these systems. We have categories of tools like optical lattices that change the potential landscape the atoms move in. So indeed, optical lattice is the iconic example, but you can have different kinds of confinement, harmonic confinement, box confinement. All of this can change dynamically. One can change the strength of the interaction of these systems using Feshbach resonances, typically just changing the strength of the 3D interaction constant. But in more recent systems, for example, highly magnetic atoms, this can be used to reveal relatively strong dipolar interactions in the resulting physics. And as will be relevant in this talk, we add terms like gauge fields, that is, potentials inside the kinetic energy part of the Hamiltonian. So today we'll be engineering optical lattices and gauge fields and not tuning the interactions. All right. So this is what I call my shameless self-promotion slide. This is how I avoid talking about everything we do in my group. So I'm here in Singapore for 2 more days after today. So if anyone here would like to discuss any of the things I've written down here, I would love to do so. I simply don't have time to talk about these things. All right. So with that, I'd like to turn now to the first specific experiment I'll talk about today, which is Floquet engineering topological Dirac bands. And this is the Floquet case, the left hand of my 2 examples. So what we're going to do is engineer a dispersion relation such as this that's everywhere linear. This is going to be an extremely clean realization of the 1D Dirac Hamiltonian. And we're going to be able to characterize this in terms of topological invariants. Okay. So hopefully as we go through this section, you're going to appreciate what I mean by each of these notions. Actually, I've been interested in 1D relativistic physics for quite some time. And I'm giving 2 examples pulled from papers that we've done on this. And what I want you to notice about these figures is that these dispersion relations cannot be described as everywhere linear. In fact, I think we can agree that they're nowhere linear. So what we do in these experiments is pick out a little region such as this square or that square, where when you zoom into it, things are approximately linear, and one can open up a gap in that regime, and we can approximate this configuration as the 1D Dirac Hamiltonian in the vicinity of this. But you can see the approximation is highly constrained in parameter space. And after doing these results, they were kind of hard to do, and one sort of loses inspiration in a almost nowhere linear dispersion relation. So I was really happy then to read this paper from Peter Zoller's group that said they had a way to, using Floquet techniques, to engineer a dispersion relation in a lattice that is everywhere linear. They framed the difficulty here in terms of symmetries of the band structure. That is to say, you have to have a fermion doubling theorem, where if you had a Fermi energy, there has to be a state there and a state there, two states, and in this case, there's only one state. But what the real physics is except for extremely pathological potentials, bands enter and exit a Brillouin zone at the same place, which implies this double crossing. So this isn't allowed. So what they said is, well, what if we allow periodic time driving as well? Which means that not only is this state at minus pi equivalent to this state at plus pi, this state at minus a quasi-energy of omega over 2 is equal, the same state, to the state shifted up by this state here. So now the way we've gotten around this in-principle issue is if you trace out this red band from bottom to top and you end up here, well, okay, that by the lattice symmetry is that point, and that by the Floquet symmetry is that point, and you've arrived at the same place again. So now at least there is no in-principle reason by which you cannot make ever linear dispersion relations. And the second thing they point out in this paper is that once you've constructed this configuration, it's associated with the Floquet winding number. And the Floquet winding number is in fact deeply connected to the structure of this dispersion relation as well. And we'll get to that at the end of the section. So this is wonderful. I was once again invigorated and super happy that it had to do with my second favorite thing, which is topology. All right. Okay, we have to do this with real atoms, though. These guys, these theorists, were allowed to think about arbitrary, a two-level system, and that was too complicated even. But we have to start with something ghastly like this. And in all of this cold atom physics, you have the wonderful tools of atomic physics, meaning we don't need to think about any of this level structure up here if we don't want to, and we can simply think about addressing the ground electronic manifold to even one group of excited states. We're going to have this 5p state, and in fact, mostly we don't even need to think about both of those. One of them will suffice. We do laser cooling, and once the atoms are cold enough, we don't need to think about any of the excited state structure anymore, and we think about the ground state electronic manifold, which is then separated into two hyperfine manifolds given by the combination of electronic and nuclear spin. And even this 6.8 gigahertz is a large energy for us. I think that's about 300 millikelvin. So we can focus on this lowest energy manifold of states. And that's what we shall do for the rest of this talk. So we're in the lowest hyperfine manifold of the electronic ground state of rubidium-87. In order to create the lattice I depicted earlier, this sort of bipartite double wall lattice, we illuminate the BEC with a pair of counterpropagating lasers. Each one of these lasers has two frequencies on it, which we'll call omega and omega plus delta omega. And we have an oscillating magnetic field. Well, what are these omegas and delta omegas? Well, we have a perpendicular magnetic field applied, which linear Zeeman shifts these three states, these f equals -1, 0, and +1. And we are resonantly coupling with a combination of two photon Raman transitions and RF fields, these three states together. If you knew the Clebsch-Gordon coefficients to this problem, you could work out exactly what's happening here. But it so happens there's a geometric interpretation as well, which is a lot more convenient. We can think about the combination of these coupling fields in terms of a spatially varying magnetic field in the sense of a Zeeman shift, meaning all of those fields can be aggregated into an effective magnetic field omega dotted into the vector of angular matrices. And the configuration I described before, this indeed is a three vector. We have a combination given a term from the average of the two Raman coupling strengths, a term from the RF strength, And over here, similarly in the y component, and the z component, when it's non-zero, is from a detuning. Now what we can see is that the only spatial structure is coming from the Raman couplings over here, and it repeats every lambda by 2, where lambda is the optical wavelength. So then we can visualize this effective magnetic field as tracing out a manifold of states, a locus of points here, as a function of position. So this is a vector that traces out an ellipse. If we start at position 1 here corresponds to a relatively long vector. And in the adiabatic approximation, we understand the energy shift associated with that as the negative term here being a relatively large negative energy. As we move along to position 2, this vector becomes shorter, and the energy becomes larger, producing a maxima in the local adiabatic potential. Over here, 3, the vector reaches its maximum length, giving a local minimum. And position 4 is the largest position in the adiabatic potential here, and then it repeats. So by tuning the relative balance between the Raman couplings, as well as the strength and phase of the RF coupling, we can manipulate every parameter of this double well potential. So this is in contrast by other techniques which frequency synthesize this type of thing using two periods of lattice that kind of obviously sum together to produce a double well potential. Here we've used an effective adiabatic potential to do this. And sort of for full disclosure, why did we do this? Because one of the things my group is very good at is using Raman couplings to synthesize potentials. If you leave this talk and say, I want to make a double well potential, I can assure you that this is one of the hardest ways to go about doing it. Okay. Nevertheless, once you've done it, we can distill this into a simple picture of particles hopping around this double well potential. And we're going to consider two configurations of the potential sort of graphically depicted on this side, where either there is a large barrier between the sites of the unit cell, which is depicted in gray, or a smaller barrier within the unit cell and a large barrier between unit cells. I'll call these configurations 1 and 2. And in this sort of schematic here, we can see there's a bonding connection between the unit cells, and here in 2, there's a bonding connection within the unit cell. Okay. I'm going to call such orientations highly dimerized lattices, meaning there's almost no coupling on these weak links. A second point now that I'd like to make here is the coloration of this curve depicts the local magnetization of these states. So I said we're following an adiabatic potential. As the atoms move in this potential, the orientation of the states on sort of a generalized 3-state Bloch sphere changes, and we can measure this. So we actually have sublattice readout capability, at least in the bulk, by measuring the MF projection of the states we have to tag eigenstates in these things. So we'll see in a couple slides, maybe one slide, how good that is. Yep. All right. So as an experimentalist, once you make a configuration like this, you sort of do some basic tests on it. And I think the easiest test we can do in this one is prepare atoms in one site, let's say the blue site here, and then suddenly allow tunneling to take place. Okay. So if tunneling takes place between this position and that position, the magnetization oscillates from -1 corresponding to the blue site to +1, back and forth like that. So we're really able to measure this motion within these individual unit cells or between neighboring unit cells. Importantly for this presentation, we can also measure the momentum of these atoms. So I didn't mention, but for experimentalists it's good to know, we do a lot of time of flight measurements in these. And by measuring the overall momentum distribution, we can find the mean momentum. And that's what's plotted in this graph here. In both of these curves, and in one below, the black curve is our ab initio lattice-based calculation of what should be happening based on separately calibrated parameters, meaning that this black wiggly curve that at short times passes through all the data is not a fit. That's just what we compute it should be doing. Given the momentum, we can integrate the momentum and determine the mean displacement of the system, giving these optical wavelength scale oscillations that are observed there. So the point is, we can engineer this, and both for fast and slow dynamics, we really understand what's going on. Okay, on to topological Dirac lattices. What's the idea? Is this theory paper complicated? If you were to read the paper, you would believe it was complicated. But this is one of these times where talking to other people is useful. So we understood this complicated theory paper. And then I went to my colleague Bill Phillips and said, okay, Bill, we're going to do this experiment. What do you think? He says, that's a good experiment. And he said, but Ian, this is really complicated. I said, well, yeah, it's complicated to understand this sort of thing. And he said, well, I don't think it's very complicated, actually. And yeah, he's right. Here's what actually is happening. So what we're going to do is imagine you start in this red state there. All you do in this whole proposal is allow tunneling to occur for half a period, exactly in the previous graph. The red atom will move over to this blue site. And then you quickly stop the tunneling, flip dimerizations, and this blue site will now move into that red site. This together forms one Floquet period. And if you started in this blue site, the reverse would happen. You'd end up in that blue site. So it's really simple, actually. You just wait a half a period of tunneling. You have half a Rabi flop between these sites. You flip the configuration, have another half a Rabi flop. And buried in all the math is something that obviously moves that blue red one to that red one, and this blue one to that blue one. Okay? So that's the entirety of the proposal in this paper. And the second half, they characterize topology, and then what happens if parameters become slightly imperfect. All right, so with that insight, we're going to do the experiment. So I'm going to give you two different protocols in this sort of A column and this C column. Now let's look at the A column. The A column is what we actually did in the lab to implement this structure. One important thing to realize is this is a real experiment, and there are higher block bands, meaning we have to change parameters fast enough that we flip instantaneously compared to the energy gap between the two lowest bands, but kind of slowly so we don't create excitations to higher bands. And this gives rise to these rather strange looking waveforms that are actual changes in the tunneling parameters. If you look at the magnetization as we do this, let's say starting in the red site, it oscillates back and forth, and basically this looks just like the tunneling curve I showed you before, and similarly if you start in the opposite state. But if we measure the momentum and integrate it, you see something quite different, which is a linear drift at the position either upwards or downwards, depending upon the initial state you started in. And this linear drift is the displacement mechanism indicating that we've created the expected linear Dirac bands. As a self-skeptical group of people, we did a complementary experiment where we followed our exact sort of complicated switching protocol, but halfway through the protocol, instead of flipping to the other dimerization, we flip back to the original dimerization. Right? If we look at the magnetization, we again see the exact same thing, but when we integrate the position, we see oscillatory motion. Okay? So actually the drift went away and it was shown by our experiment. Curiously, when we compute the band structure for the second case, there's a quadratic touching point. And for those of you with a condensed matter background, this is like bilayer graphene, where the Dirac point gives rise to this sort of quadratic fake Dirac point. So here's an accidental scheme by which we can create these sort of quadratically Dirac-like systems using Floquet engineering. All right. Now, kind of amazing, even to us, is if you zoom in to these data and look at the theory sitting on top of the data, we see not only exactly the right slope, but even some pretty good representation of the subperiod structure as these atoms go within these half Rabi flops, both up and down. And we see a very good agreement as well in this sort of dimerization preserving configuration. Okay, so we understand what we're doing. With that said, I would like to make a quick detour to something I didn't mention, and we're going to use atomic Zitterbewegung as the foil to understand this. So what is Zitterbewegung? Well, it's a concept introduced in the beginning of quantum mechanics, which said if you have a relativistic electron and you compute properties of it, like it's the expectation value of its center of mass position, and compute the time evolution of that, you discover that it can undergo a microscopic trembling motion called Zitterbewegung. A couple of years ago, this is one of the first Dirac physics papers my group did. We directly observed this Zitterbewegung in an experiment, and I'd like to break the news to you. Actually, it's just Rabi flopping. This is another phenomena that is cloaked in mystery, but in atomic physics we understand as Rabi flopping. So all it really is to say you have a bare Hamiltonian that has this linear dispersive feature, and if you start in an eigenstate of that and suddenly turn on the mass term, what does the mass term do? Well, it gaps this, it couples them together. It's a field along sigma x, you origin along sigma z, you process around that axis, and microscopic trembling ensues. Okay, so that's all Zitterbewegung is this sort of microscopic oscillation. All right, but where is Zitterbewegung in our system? Well, what I didn't mention to you, although I hinted at it, this switching protocol we have, where we allow half periods of tunneling in one way, then a half in the other, is a fine-tuned protocol. What if you slightly change the experimental timing? In fact, this is hard in the experiment to get right. Well, then you don't quite do a full half Rabi flop before you switch, and if you do twice, you're certainly not going to end up moving 2 sites over. Something else is going to happen. And that thing that happens is the spectrum develops a gap right at the origin, opening it up, inducing a small mass into the situation even when you try to close it. If you measure now the position as a function of time with this new switching protocol, you see oscillatory motion, Zitterbewegung. So we've introduced a mass into this problem, and what this graph is showing you is the size of the mass gap as we approach the fine-tuned Floquet period, showing, given our fine-tuning, how small we can actually make it. The black dashed line is what you compute, assuming a perfect protocol. And here is a computed Floquet spectrum for the orange circled point, showing the gap that's opened up in the spectrum. Right. So this is to say that this experiment is hard. It's a fine-tuned problem, and this fine-tuning is associated with sort of an emergent symmetry in the system, which is going to be relevant in the final portion of this section. All right. So what did I show you? Well, we moved atoms from site to site in something which is basically the same as a bucket brigade. And what does this have to do with topology? Well, now we have to look at more than just the energies. We have to look at the states. So in order to look at the states, we chose to do an absolute brute force technique. And what we're going to do is fill the lowest block band and do quantum state tomography on the system to measure the orientation on the block sphere of every state in the block band at every time in our pumping protocol. So we're really going to just learn what the state is, and that's going to be sufficient to fully characterize the topology. So really quickly, to give an idea of how we did that, we use our quantum control tools of this lattice to manipulate the state orientation to give us measurement along 3 different projections. So the idea is our native measurement basis is a sigma z basis. If we want to measure, let's say, sigma y, we can perform a rotation around sigma x. How do you do that? We change the tunneling strength. That's a sigma x term, and we can rotate y to z. If we want to measure the x projection, how do we do that? Well, we tilt it a little bit and turn on tunneling, which gives it a rotation around this 45 axis that transforms x to z. So in order to get the points I described, we're going to do 3 separate repetitions of the experiment with each of these 3 different readout protocols in place after having filled the Brouwer-1 zone. Okay? And this gives us the full orientation on the block sphere. Okay. Let's see. So I'm going to start with this. This is the result of this kind of quantum state tomography. This column is a theoretical calculation, and these are our direct observations as a function of crystal momentum vertically and the evolution time horizontally for 1 period of our drive. Earlier I said we're going to measure topology by integrating over some manifold. This 2D manifold, when you glue the top and bottom together and the beginning and the end, is a torus. So we're going to be integrating over the 2D manifold of a torus. We need a vector field as well. What's the field we're going to integrate across? Well, the field is the Berry's curvature or the elements of the quantum geometric tensor. In this case, we have a 2D manifold, so the Berry curvature has a component perpendicular to this manifold, which is given by this combination of derivatives. We know the state at every crystal momentum. As a result, we can take derivatives both as crystal momentum and as time to obtain the Berry's curvature. Now, a thing I did not mention to you is that this topological invariant is also equal to an integral over the energies, which was first presented in this paper. Now, this is actually a really astonishing result. This says that in order to get this particular topological invariant, it suffices to only know the crystal momentum dependence of these energies. Okay. Now, what does this specifically say? Well, okay, we're going to integrate over the Brouwer-1 zone of the crystal momentum derivative of the energy. Well, wait a second. That's integrating the derivative with respect to Q over Q. Surely that has to be 0. Well, actually, it measures the entry point and exit point of these states as they enter and exit the Brouwer-1 zone. So this topological invariant simply counts how many repetitions of the quasi-energy band did this state go as you traverse it. So for the sort of trivial case where you enter and exit in the same place, this would be 0. In our case, we're expecting +1 or -1. All right. So I have one more thing to tell you. This is not directed to the theorists in the audience. Don't trust an experimentalist who differentiates experimental data. This is typically not the best maneuver in the world. So indeed, when we differentiate the experimental data, this I thought looked pretty good, and it seemed to correspond pretty well with theory. We differentiate it. I think we can agree that these only have a passing resemblance to our numerical computations. However, the saving grace is that what we're going to do after differentiating the data is integrate it over the Brillouin zone again, thus undoing the damage we did. And completely astonishingly, if we study the time evolution having filled the band and the configuration corresponding to a upward going slope, this integral gives a winding number extremely close to the expected value of 1. Okay. So this is a no cheating measurement of topological invariant that's super close to 1. If we go the opposite direction, it's super close to -1. And if we perform the configuration that doesn't have any pumping at all, it's within the uncertainties of 0. All right, so this sort of brute force method of measuring every state at all times is an extremely effective manner to really characterize a topological invariant in terms of its fundamental definition. Let me see if okay. So I have one more comment on this slide. So for those of you, I don't know how many of you have really thought about topological pumps before. This topological characterization is exactly the same for a Thales pump. So these are the adiabatic topological pumps that if you slowly deform parameter space, you'll see displacement given by some kind of winding number. Well, it is the same winding number. The difference is that the Thales pump exists in the limit of drive frequency goes to 0. This pumping exists in the limit when drive frequency exactly matches the Floquet period, or the tunneling period equals the Floquet period. So actually the Thales pump is also a fine-tuned protocol, but it's fine-tuned as omega goes to 0. But the topological characterization is identical. All right. So for the last maybe 10 minutes or so, I'd like to give a brief description of what happens in time-evolving systems when you directly quench from one Hamiltonian to another Hamiltonian. In some sense, this half of the talk is a little bit simpler. There's no Floquet at all. There's just a ground state of one Hamiltonian and time evolution under another. We're once again going to be thinking about the same model I had before. Let's name it the Rice-Meili model. We're going to have a tilting term that now tilts the energy difference between these minima, which we didn't have to think about before, as well as the tunneling in the two different dimerizations. But I'd like to delve a little bit deeper into the eigenstates of these Hamiltonians now, since that's going to be relevant for the initial state. Just as I gave the adiabatic potential in real space as a way to organize our thoughts about what the potential was going to look like, we can diagonalize this lattice in momentum space also in terms of a momentum-dependent effective magnetic field. There are 3 terms. Once again, the third term, the z component, is the detuning given by the tilt difference between these wells. Once again, it depends sinusoidally and cosinusoidally in terms of a variable, but now the variable is crystal momentum. We have one term, J primed, which is characterizing the tunneling within the unit cell, and J, which is characterizing the tunneling between unit cells. Okay. If one diagonalizes this, one arrives at an energy spectrum which looks something like that. Right? This gap will be present at all times except when J equals J primed and delta equals 0. I'm going to call the configuration 2, that is when J primed is large and J is 0, to be the topologically trivial configuration. You can see that this now corresponds to eigenstates which are going to be independent of crystal momentum. There's no more crystal momentum dependence here. It's going to give a dispersion relation that looks like this. And if we say what are the orientation of these states, they will always be along sigma x. We used exactly the quantum tomography readout we developed in the previous result to measure this. So these are experimental data showing us the measured orientation on the Bloch sphere of all the eigenstates, and here are the three components as a function of crystal momentum. If we flip the dimerization, the eigenstates stay exactly the same. But if you look at the eigenenergies stay exactly the same, but now the Hamiltonian encircles the equatorial plane of the Bloch sphere, and we can see that as we read out the eigenstates as well, here in terms of the components. So we're going to call this a topological phase. And in a couple slides, we'll get to why I'm labeling it as such. In order to really diagnose what's happening in this, we need to characterize the system in terms of its symmetries. So we're going to have time reversal symmetry, which says, is there an operator T under which the Hamiltonian's complex conjugate is transformed to itself? The most trivial example of this is the one we're going to use, which is to say, we'll use the identity for this and to say, is the Hamiltonian equal to its complex conjugate? We can see that if this tunneling phase that I haven't mentioned yet is 0, that's the case. We'll be able to introduce that if we want to. Next, we're going to have particle hole symmetry, which is roughly saying is the upper band equal to the lower band. And we have a chiral sublattice symmetry, which says is the left side equal to the right side. With these symmetries in place, we can begin to understand a little bit more about what's going to happen with this system. I'm going to characterize it in terms of two topological invariants. The first one is going to be the Zach phase. So in the limit where the tuning parameter is large, we will not have particle hole symmetry, we'll not have chiral sublattice symmetry, but we'll still have time reversal symmetry. We're going to look at an initial state where the tunneling phase is non-zero, which will break time reversal symmetry, which will break particle hole symmetry, but will preserve chiral sublattice symmetry. And we're going to look at the so-called the standard SSH, which has no tunneling phase and no detuning, which will preserve all three symmetries. We're going to see two kinds of topological invariants. One is the Zach phase, and another one is a winding number. The Zach phase is either going to be any number with the symmetry class, or Z2 for the other two, and the winding number is going to be any Z. Okay, how are we going to measure this? Okay, so this is the sort of basic Rice-Meillet picture showing what you'd see in a charge pumping kind of configuration, plotting the Zach phase as a function of all parameters, showing that it's only integer valued exactly when this detuning is 0. Returning to our experimental data I presented before, actually we can see this immediately. What the Zach phase is really doing is measuring the area either above or below the trajectory on the Bloch sphere traced out by the eigenstates. So in this case, in the topological case, the eigenstates trace out a circle on the Bloch sphere. The upper half of that has an area of 2 pi corresponding to a Zach phase of pi. The topological trivial phase doesn't trace out anything, corresponds to a Zach phase of 0. These numbers are experimentally obtained values by integrating over this. I'll tell you in a second a catch. There's a second quantity as well, which is a chiral winding number. This asks how many times do you encircle the equator of the Bloch sphere if you follow the states around, which is a subtly different question than asking how much area is enclosed. In this case, we maintain a chiral winding number of 1 and 0 in this case. This is the second time in this talk where you should not trust an experimentalist. Don't trust an experimentalist who's measured an integer. We measure real numbers. So what's going on here? Well, the chiral winding number is only strictly defined when every one of these points exactly lies on the equatorial plane of the Bloch sphere. So you require chiral symmetry for that. So what we've done in order to measure integers is to project these experimental data points onto the equatorial plane and then count the winding number. Okay. So that projection process enforces an integer criterion. And this is not useful. Well, one cannot assign an uncertainty to that number because of the projection process. All right. Let's do some quenches. We're going to quench from the large delta Rice-Meillet eigenstate, which had only time reversal symmetry, into the standard SSH model, which has all three symmetries. Yeah. So we directly measure the crystal momentum dependence of the point states in the Bloch sphere as a function of crystal momentum and evolution time. These pictures are showing the important thing. If one is evolving according to the topological SSH model, remember there's two configurations. All the states start in the down configuration. That's the eigenstate of the large delta. They move upwards. As they do so, they encircle the equatorial plane of the Bloch sphere before coalescing on the top. If one instead evolves in the trivial configuration, these move together, grouping along an arc, finally coalescing once again on the top of the Bloch sphere. Integrating those experimental data, we can obtain the Zach phase as a function of time, which is only defined anyway modulo 2 pi. In the topologically trivial case, it stays at 0, and having done phase unwinding in the topologically non-trivial case, it starts at 2 or 0, smoothly changes at this point and encircles the equatorial plane of the Bloch sphere, becomes 1, and then drops to 0 when it coalesces at the top and oscillates back and forth. Okay. A second experiment one can do is quench from the eigenstate of a time reversal symmetry broken case into the standard SSH. And the only thing I want you to take away from this is it's complicated. And if you look at the time evolution of the Zach phase, it does something. And the point I want to make here is that in general, when you quench from one Hamiltonian to another, nothing generic happens. Physics happened, we did a numerical simulation, and something happened. Okay? Are we surprised? Not really. We changed the symmetry class of the Hamiltonian from one symmetry class to another symmetry class that supported different topological invariants, and we had no expectation that something should stay the same. Okay, so it's complicated. So what did we learn from Max and Nigel's paper? Well, they said, what happens if you quench between different topological configurations of Hamiltonians that have the same symmetry? Well, we can do that too. We can quench between a topological and non-topological configurations of the SSH model. Okay, these have different topological characterizations. One's trivial, one's non-trivial, but the symmetries are the same. So if we do this, what do we expect now? Should the Zach phase stay constant in time? Should the winding number stay constant in time? Let's find out. Okay. So we'll quench between trivial and non-trivial. We're going to go both ways. No? Okay, we measure quantum state tomography, and something happens. But the important thing is captured by these two panels here. So if we quench from the trivial, from the non-trivial to the trivial phase, the original eigenstates traced out a circle on the equatorial plane of the Bloch sphere. We now have a Hamiltonian corresponding to just J prime along one direction. This circle simply rotates. If it rotates, you always trace out a half sphere on the Bloch sphere, and the Zach phase is unchanged. Okay. If one starts in the trivial phase and quenches into the non-trivial phase, one has a little bit of a more complicated evolution where you start out with a point, and this point expands into two loops that sort of half encircle the top and bottom of the Bloch sphere. To me, I guess given my age, it resembles Pac-Man. Sort of going to eat the Bloch sphere, right? But these actually have opposite orientation. So the Zach phase also should stay the same there. And when we integrate it and plot both the expected Zach phase as well as the measured Zach phase, we see that, well, the measurement isn't exactly constant, but it's relatively constant from here to here. However, and this is the kicker, the winding number changes discontinuously. So I mentioned before that the winding number really is only defined when chiral symmetry is preserved in the state. I've plotted with these gray bars when the winding number is actually a reasonably well-defined quantity. So for example, if we start here, sorry, let's do this one. Start in the non-trivial phase, evolve according to trivial Hamiltonian, the winding number alternates from +1 to -1. This makes sense. You had a circle, and basically half period later you flipped it over. So now you trace out in the opposite orientation, and you get a minus sign. But even more interesting is if you start in the trivial phase and evolve to the non-trivial Hamiltonian, the winding number is started at 1 point and jumps discontinuously to 2. This is because when Pac-Man's mouth closes, you encircle the Bloch sphere twice. So what we've been able to do here is change the winding number to something which is not supported by an eigenstate of the SSH Hamiltonian at all, but is consistent with the symmetries of the Hamiltonian. In fact, this is associated with an eigenstate of an extended SSH Hamiltonian with next nearest neighbor tunneling. So altogether, this shows you that there's a wide variety of things that can happen when you study free evolution. But in particular, there are strong constraints on what the symmetries are, what the topological invariants are allowed to do when you quench between phases of exactly the same symmetry classes. And that is the conclusion of Max's paper and our experimental findings. So with this, I want to sort of pop up a conclusion, which is really an outlook. Everything I told you today was about non-interacting systems. And non-interacting systems are things that you can, in principle, compute on a computer. So if we had known the answer to this experiment beforehand, we could have gone and computed it. The understanding we get from this kind of experiment is really understanding better how we organize topological systems before knowing what the answer is. But I think one of the really interesting questions we can get at is, okay, what happens if we now perform similar quenches and strongly interact in topological systems? The example I give as sort of like a leading example is an old theory paper that Jay Sao and I did together, where we asked about adiabatic quenches between topological and trivial phases of P-wave superconductors. So this is not the same paradigm, and what we found in this is that when you go through this topological transition, you can see basically Stuckelberg oscillations appearing that are giving information about the opening and closing of the topological gap. What would happen is if this experiment, if we cross it instantaneously and looked at the associated dynamics? Because again, this is another system described by exactly the same symmetries and the two phases, but two different topological classes. So I think that there are neat questions we can ask for interacting systems as well. And with that, I'd like to conclude, and thanks for your time.